Greetings. Welcome to Machine vs Mathematics channel. You have a linear constant coefficient difference equation. Okay? And based on this linear constant coefficient difference equation, you would like to design a discrete time system. So you have, for example, couple of options: direct form 1 design, direct form 2 design. Which one do you choose? So there is no second thought. We obviously choose direct form 2 because it requires less memory when compared to direct form 1. And the same DF2 we use in cascade form and in parallel form as well, okay, for further optimization of our discrete time system design. So in that scenario, you have a simple question. You have a simple question based on finding out the poles of the system transfer function. So we can construct as y of n is output and x of n is input. So they're establishing a link between input and output, and this fellow is our system. Okay, so this fellow is our system. So I have input here and output as well. Okay, so now so end of the day he's asking like this. Now he's asking us find the poles of the system transfer function. Okay, or the poles of the system transfer function are located at. So we should be able to find one out of this 4. This is asked in GATE ECE 2015 set 1 for 2 marks. See, this is a direct question. There is no big twist in this. First of all, there is no twist in this. So sometimes we can happily attack questions like this. So now, first of all, what to do? If I would like to locate the poles of the system transfer function, so I must take system transfer function like this, h of z. So h of z is output transform over input transform. So x of n is input, y of n is output. So this we should be able to find. Okay, and the denominator quantity, they accommodate poles. Numerator quantity will accommodate zeros, and poles will influence the system's magnitude response, and zeros will influence the system's phase response. Okay, so anyways, we have separate lectures on these things. For now we will focus on this question. All right, so before we find h of z, we should be able to construct link between output and input. So to construct that, you have a system like this. So this is what? This is y of n minus, this is also y of n, this is also y of n. So here also you have y of n. Okay, now this z power minus 1, what is this z power minus 1? For example, you have some quantities. Say I have something like some g of n. I'm taking some input as g of n. Now output is what? It is simply g of n minus 1. So therefore this is my memory block, or simply we could say this fellow will introduce unit delay, yeah, in the output. So input is g of n and output we have g of n minus 1. So therefore we have y of n here. So what we get now? We get y of n minus 1. So this, at this node you have y of n minus 1. Okay, now again you see arrows are not given, but you have to understand this. Now this y of n minus 1 is going, say it is present here and also here now. Okay, now this is what here. Now this is a scalar quantity 5 by 6. So multiply 5 by 6 to this y of n minus 1. So we have this, and again this is y of n minus 1. You have one more unit delay here, right? So therefore y of n minus 1 undergo this, and you will get now y of n minus 2. Alright, so y of n minus 2, here also we have y of n minus 2. Now we have to multiply negative 1 by 6 with this y of n minus 2. So therefore you have here minus 1 by 6 y of n minus 2. Now what do you have here? X of n plus minus 1 by 6 y of n minus 2. We have like this. This is minus 1 by 6 y of n minus 2 plus x of n. Okay, and again this fellow, so this fellow is added with this fellow. Alright, because I have summer here, right? So I can add these two. I can add this quantity with this quantity, and that is what our y of n. So finally, what is y of n now? So y of n equal to, so we have reached here, right? Minus 1 by 6 y of n minus 2 plus of course I have x of n. So this part is done. Now we have to add this branch quantity, okay? Because we have again summer here, so therefore add that fellow as well. So you have 5 by 6 y of n minus 1, and this is what the connection between input and output. All right. So this is a simple thing we have. Now what do? Now you simply apply Z transform. So applying Z transform. Say, how do you apply Z transform? Directly we can apply, right? So we have the flexibility, we can apply it directly. Let me take one more page. So let me revisit my linear constant coefficient difference equation. See, this is what difference equation, and you have constant coefficients. These coefficients are independent of time. We don't have time dependent coefficients, otherwise we can't analyze LJ systems using Z transforms that easily. Okay, so let me put it down like this. So I have minus 1 by 6 y of n minus 1, and also we have plus 5 by 6 y of n minus 2. So minus 1 by 6 y of n minus, this is 2, right? Y of n minus 2 plus 5 by 6 y of n minus 1 plus x of n. Okay, so this is what you have. Now this is what we have, and just apply Z transform. If I apply Z transform, we get y of z equal to minus 1 by 6, and you know very well z power minus 2 y of z plus y by 6, as I have n minus 1, so z power minus 1 y of z plus x of z. And you should know this. For example, you see, I have a sequence, discrete time sequence x of n. You take its Z transform, you have x of z. Okay. Now if I introduce a delay k units in the time domain, this will be nothing but what? Z power minus k multiplied by x of z. And if I have x of n plus k, so now in the exponent we have now z power positive k x of z. So bearing these things in mind, we can construct Z transform for the above linear constant coefficient difference equation. Okay, now take all y of z one side, x of z to other side. So you have y of z multiplied by 1 plus 1 by 6 z power minus 2 minus 5 by 6 z power minus 1 equal to what we have. On the right hand side we have x of z. So end of the day we need what? Output transform over input transform. This is what our system transfer function h of z, and this is nothing but 1 by 1 minus 5 by 6 z power minus 1 plus 1 by 6 z power minus 2, right? So this is very simple. So I can directly factorize this denominator. If you are worrying in terms of negative powers of z in the denominator, you multiply and divide by z square. Okay, so therefore you get like this: z square minus 5 by 6 z plus 1 by 6, and I can factorize this happily. You get z square over, so we get z minus 1 by 2 multiplied by, you get z minus 1 by 3. So from this, what do we say? The poles are located at 1 by 2 comma 1 by 3. So z minus 1 by 2 equal to 0. Z minus 1 by 3 also equal to 0. If you make so, then h of z, we are having poles at locations, say 1 by 2 comma 1 by 3. So at locations 1 by 2 comma 1 by 3 we have poles for this. Simple. discrete time system, linear constant coefficient discrete time system is this. Okay, and that's it for today. So thank you.